The journey to MHC, a simple story. The old road, residual connections. Once upon a time, there was a smart robot brain learning to think better and better. Inside this brain were many floors stacked one above another. On each floor, the brain learned something new. But there was a problem. Sometimes, when information climbed many floors, it would forget where it came from. So the brain invented a shortcut road. Instead of forcing information to go floor by floor, it said, "Hey, old idea, you can come directly with me." This shortcut was called a residual connection. So every floor worked like this: learn something new, add the old idea, move ahead safely. This worked beautifully. The brain became deep, smart, and stable. The new idea, hyper-connections, HC. Years later, scientists said, what if one road is not enough? So they built multiple parallel roads instead of one. Information could travel through many paths at once. This was called hyper-connections. Now the brain said, you go left, you go right, you go diagonally, you mix and regroup. The brain became even smarter. But a new problem appeared. The big problem: chaos on the roads. Because there were too many roads and no traffic rules, strange things started happening. Some information became too loud, some became too weak, some got lost completely. When the brain became very deep, signals exploded or vanished. Training became unstable. The brain started forgetting again. The wise solution, MHC. Then came a wise idea. Let's keep many roads, but add strict traffic rules. This new system was called Manifold-Constrained Hyper-Connections, MHC. The rules were simple. No road can steal all the traffic. No road can block traffic. Everyone shares fairly. Total traffic stays the same. Now information flows calmly, mixes nicely, never explodes, never disappears. The brain became deep, stable, powerful, and that is the journey to MHC. Now let's open the box and see how MHC actually works, step by step. 1. What was the core problem? In normal residual connections, output equals input plus new thing. This is safe because input always passes unchanged, signal strength stays balanced. In hyperconnections, input is split into many streams. Streams are mixed using matrices. But these mixing matrices were unconstrained, so when many layers stacked, mixing ties mixing's mixing, signals got multiplied wildly. That breaks the identity property, the original signal stays safe rule. 2. The big idea of MHC. MHC says, we still want mixing, but mixing must be well behaved. So MHC forces the mixing matrix to live on a special shape called a manifold. That manifold is made of doubly stochastic matrices, meaning all values are non-negative. Every row adds up to 1. Every column adds up to 1. Think of it like sharing a pizza. Everyone gets some, no one gets extra. No slice disappears. Why is this so powerful? Identity is preserved because totals stay the same. Information does not explode. Information does not vanish. Even after 100 plus layers, the signal remains stable. Stability across depth. A magical property. Doubly stochastic multiplied doubly stochastic equal to doubly stochastic. So even when you multiply many layers, stability is preserved forever. This fixes the biggest HC problem: controlled mixing. MHC still allows information sharing, cross-stream learning, rich interactions, but in a safe and bounded way. How MHC enforces the rules. MHC uses a famous algorithm, Sinkhorn-Knopp algorithm. What it does, takes any matrix, makes all values positive, normalizes rows sum to 1, normalizes columns sum to 1, repeats this many times. Result, a perfect doubly stochastic matrix, so every residual mixing step is forced to behave. But isn't this expensive? Good question. MHC adds only 6 to 7% extra cost. Why? Fused kernels, smart recomputation, efficient memory usage, overlapping communication. So it scales to very large models easily. Thank you for listening. Please subscribe to my channel for more such videos.